So conservation of momentum. At this point, we've already discussed and talked about momentum just as a concept and impulse as the connection between one state of an object's motion and another, taking Newton's second law of motion, F equals ma, and converting it into the much more descriptive F delta t equals m times delta v, all as vectors, of course. And in this equation, we're calling the left-hand side the impulse, and we're calling the right-hand side the change in momentum. Let's call that delta p for here. And what we want to do now is expand on this to a before and after. It's nice to be able to describe what's happening for an individual object. Let's say that we have something that has a force acting on it for some time, and we know that specific mass is going to change its velocity by a specific amount. But when we look at something like this video and pivot interactives, where the dart is ejected at a particular velocity, it embeds itself in the foam block, and then the cart moves along with the dart stuck into it. And we pick another trial here that's got a little bit more smooth. Two things are very clear. The dart has to slow down after contact, and the cart has to speed up. So we have a situation where there's two different objects, and they're both experiencing a change in velocity. So we could do two different calculations here for impulse and change in momentum. However, that would be unnecessary. We don't need to do all that. We can come up with a formula that's going to allow us to do calculations for both objects at the same exact time. So if we just grab a screenshot of this and paste it over here, we can do a little bit of drawing on what's happening. At the moment that there's contact, we initiate and begin a force. And we can say that right here where the dart and the cart are making contact with each other, the dart is going to experience a force acting backward on it. So we're going to put this as force on dart. And we're also going to have a force that's acting on the cart at the same exact time. And because of Newton's third law of motion, we would say that these two forces are equal in size and opposite direction. Obviously, they're opposite in direction because the force acting on the dart needs to slow it down, so it has to go against motion, and the cart needs a force acting in the direction that it will move. But it's really, really important here to understand that the forces have equal size, but they have opposite direction, and they're acting for the same exact time. If we were to, try to piece together what's going on here, the amount of time, sorry, that color marker is just not going to work. The amount of time that we have here that force is acting on the dart is going to be equal to the amount of time that the cart is having a force act on it. At some point, they stop moving. There's no more friction force, and the accelerations cease. But for that time, that's equal for both, they're both going to experience equal and opposite forces, which means they're going to be experiencing equal and opposite impulses as well. And that's the key for conservation of momentum. If we establish that the two objects are going to experience equal and opposite impulses, then we can also say they're going to experience equal and opposite changes in momentum. Now, we can get into some pretty strict derivations here, but if we were to say that the change in momentum for the cart is equal to the opposite of the change in momentum for the dart, we can establish an idea that's kind of an exchange rate, that if one losses another object's gain, then there's no net change overall. So if I've got person A and they hand over money to person B, this person's going to have, say, negative $10. This person's going to have positive $10. There's no change in the overall money there. The total stays the same. So we can consider that the total dollar value before the exchange equals the total dollar value afterwards. We can set up an idea for momentum based on that same concept without getting into too much of the nitty-gritty details of, writing out every single step of a derivation. So with this idea that forces being equal and opposite for the exact same amount of time, we get equal and opposite changes in momentum. One's going to lose momentum, the other's going to gain it. It doesn't visualize as equal changes in velocity because while we can have, we'll do magnitude of the change of momentum is equal for both. This is the dart and for the cart. We have a small mass for the dart, which means you can have a very large change in velocity. It's going to slow down quite a bit. And then that would be equal to, neglecting the magnitude bars, the very large mass of the cart multiplied by its small change in velocity. The product of those two values has to be the same, but we can have different amounts for each. So let's establish what we're going to say is the conservation of energy equation. We're going to say that the sum of the momentum, off screen here, got to scroll, bloop, bloop, bloop. The sum of all momentum for all objects initially before some sort of interaction with objects, particles, is going to be equal to the sum of the momentum afterwards, the final momentum. And since momentum is mass times velocity, we can expand this equation and say that it's going to be P1 plus P2 plus dot, dot, dot. Put a little initial parentheses there, is going to be equal to P1 plus P2 plus dot, dot, dot in the final scenario. So if you got 10 particles, you're going to have 10 terms in this equation right here. If you only got 2, which is most of what we do in physics problems, you're just going to have P1 and P2. So this is the idea for conservation of momentum. But we're going to go ahead and sub in that P is equal to M times V. There's no reason in writing as P's all over the place. So the real full formula is going to be M1 times V1 plus M2 times V2 plus dot, dot, dot on the initial side equals M1 times V1 plus M2 times V2 final. And again, most of the time we're just going to be using 2 particles, so that's where we're setting up the equation here. Now what's important here is that these are vector quantities. So each of these velocities can have x and y components. If M1, let's say it's the dart, is moving along at some positive x velocity, we might write that as, for example, something like 3 meters per second, comma 0. If it was hit something that was already moving, but in the y direction, that velocity there for the second object could be 0, comma 7. They don't have to be in line with each other. This is conservation of momentum using vectors. We can have things in any direction. Now, that's going to be very difficult to figure out what's going on here unless you know, for instance, one of the objects stops or that they're stuck together, in which case we can write some special case scenarios and special case equations. So the main situations we can arrive at are things that we can just imagine. We can start with 2 objects that are initially separate from each other, and then after some sort of interaction, we'll usually call it a collision, they are separate again. And we will call that bouncy. This is the non-scientific term here. But bouncy, if we create a little table here, initial and final. Bouncy is, sorry, let me write this a little bit lower. Bouncy is when things initially are separate from each other, and then after the interaction, they're still separate. Second type of interaction we can have, I like to call sticky. And sticky is when they are separate in the beginning, and then they're stuck together. Very creative term, right? Sticky. Stuck together afterwards. And finally, we have my favorite, which I like to call explodey. Got to end with a Y at the end there. And that's when things are together in the beginning, and then they're separate in the end. So some examples of these bouncy would be two billiard balls or pool balls colliding on a table. Sticky would be, well, something like the Pivot Interactives, where the dart and the card are separate in the beginning. After they interact, they're stuck together. And explodey would be something like, I don't know, a teacher standing in front of the classroom holding a medicine ball while standing on a skateboard. And then after they throw the skateboard, they're separate. So many different scenarios can fall into these three different broad categories. And of course, these are not highly scientific terms, but they are descriptive that'll help us solve problems that we can then categorize a little bit better. To help demonstrate that a little bit better, we have here a PhET simulation. And in this case, there are two objects. They're going to be moving towards each other. They're separate in the beginning. And I have the elasticity set to 100%. Now, this is going to be super duper bouncy. If I click play, they're separate in the beginning. They're separate in the end. This simulation is already going through and doing calculations to figure out where things are going to go. If I were to turn it from elastic down to completely inelastic, when they collide, they stick together. So somewhere in between, things can, well, they can bounce apart, but they don't bounce apart as well. They kind of go slowly. And anything that's not perfectly elastic, we call inelastic. But there's really three types of collisions you can have here. You can have the perfectly, let's go ahead and change that over here. Perfectly elastic, where they bounce off of each other. And in that case, we're actually going to have kinetic energy conserved. We can have perfectly inelastic. Keep doing that where I forget to reset it. Where when they come together, they stick. And then someplace in the middle where they kind of bounce off, but not that well. And that makes it a little complicated in terms of figuring out what equation to use when solving a problem. So that's why I like the terms bouncy, sticky, and explodey. They're very, very descriptive. And if we take this big formula and just treat it with two particles, we can write equations for bouncy, sticky, and explodey that are pretty simple to follow. So for bouncy, we would have the equation m1 times v1 plus m2 times v2 on the initial equals m1 times v1 plus m2 times v2 final. And some people prefer to write this with like A's and B's instead of 1's and 2's, and then instead of an I and an F, they like the 1 and the 2 there. Initial and final, let's just stick with that. Some people prefer to put this double subscripts on the velocity, so it's V1I and V2I. That just gets complicated. So let's just put them in parentheses. Everything initial stays in here. Everything final stays in there. Forgot my arrow on V2. Well, what about sticky? If they're together in the end, well, essentially, if they're together in the end, this velocity 1 and this velocity 2 are the same. So we could factor it out and just call it one single velocity. The two masses will be moving at one speed. So for sticky, we can write the equation, same in the initial side, m1 times v1 plus m2 times v2. Initial will be equal to m1 plus m2, kind of factoring out the final velocity. And since it's the same for both, we'll just call it vf. So there's one final velocity there. And lastly, the explodey, we just flip it from the sticky. They're not sticking together, becoming unstuck. So I guess it's an unsticky, but I like explodey. Explodey sounds cooler. So m1 plus m2 times vi, some initial velocity, will be equal to the m1 times v1 plus m2 times v2 final. Fix that right there. So that's the three types of conservation of momentum calculations we can do. I mean, technically there's infinite numbers of calculations because you can have 4 terms and 3 terms and whatever, but this covers just about all the bases. You have 2 particles interacting, and then their momentum total has to stay the same, either with them separate in the beginning and at the end, separate in the beginning and then they collide and connect, or separate in the end but they were together in the beginning. So we're going to take a look at some example problems for how to solve these things in a second video, because this one's already 15 minutes long. So tune into that one next.